Okay, so let us continue. This example we just started, uh, these type of buses means basically nothing but a bundle of wires, okay, and this could be very large because if you have a 32-bit computer, your signals, all your data, right, is 32 bits wide, and if you have 64-bit, it's 64-bit. We don't have 128-bit yet. I don't think it will go there either, but 64-bit is a lot, right? Which means that every number that you're transferring is 64 bits wide, and you cannot have many of these because it will occupy too much area. So what the designers have done, they have multiplex. You might have heard of this term before. There are multiplexers. This is a multiplexer, right? Here also is a multiplexer, and one of the requirements is that if one of the units. So the typical example for the buses in microprocessors is memory and data. Either the bus is carrying memory addresses or it is carrying the data. So to switch between one and the other, we can do it by means of a control signal. So the control signal will decide whether this memory is having an output or it is disconnected. And if memory is disconnected, data should be connected. Otherwise, this will be at a floating value. It will be at neither 0 nor 1. So this type of circuit can be implemented using what is called as a tri-state gate. Okay, very simple connection. Let us look at one example. Okay, so this is the circuit, and a new signal has come. Enable signal will determine whether the output of the gate is a natural function or it is disconnected. So that is why they are called tri-stage, because the outputs can have three values. Where are the three values coming from? Through the natural function, it can have two values. What are the two values? 0 or 1. If the gate is not enabled, then the output will have the third value, which is called as Z. Z is in some ways not a good value if that is the only value. Okay, like we said in this example, I'm not allowed to put Z on any gate. Okay, that is a signal cannot have a value Z, but the output of a gate can have value Z, which just means that it is disconnected. Some other gate is responsible for driving the signal. So that is what we will see here. Let us analyze this. Okay, enable equal to, first we will see enable equal to 0. So enable equal to 0 means NMOS transistor is off, and here I am giving enable bar. So PMOS transistor is also off. So in both the cases, the output is tri-stated, it is disconnected. When enable equal to 1, NMOS is conducting. Here I am giving enable complement, which means PMOS is also conducting. Okay, so in that case the output will be, if I give 0 I will get 1, if I give 1 I will get 0. So that case, so this is a tri-state inverter. Tri-state inverter, okay, I think this is the circuit symbol, not so important, but we can use these when we have these types of situations. Okay, so one question I had asked in the class, any general function, okay, inverter. I might want the same functionality for a NAND gate, for a NOR gate, for XOR gate, for any gate, right? How do I do that for any general this thing? Very simple, okay? Just look at this part and similar to static CMOS, okay? Only thing is, instead of directly connecting the pull up network and the pull down network to the output node, you put it through the enable transistors. So enable transistors will either allow the gate to operate in a normal fashion and drive the output, or they will disconnect the output from the input. In that case, it is tri-stated. So this class of circuits are called as tri-state gates. Okay. Okay. So next class of circuits is okay, sequential circuits, and sequential circuits are different from combinational circuits. Many times we have read this thing, because the functionality depends on the previous input also. So in some ways we get memory functionality, and many classes are there of sequential circuits. In traditional uh, microprocessor design, okay, pure sequential circuits are there. There are pure sequential circuits, not pure, I mean not really pure, but pure sequential functionality is there, okay? And if you ask where is that type of functionality where only memory is used, the best example is control logic. So if you remember microprocessor or computer organization, there are three units: memory, ALU, and control. Okay, memory is of course memory, and memory uh, doesn't, if you, in the traditional sense, memory is not a sequential circuit, because the output doesn't depend, it does depend on the previous input. So if the previous input is your data, that will be the output, but we can always rewrite it to any other number. It doesn't depend on the previous input that way, okay? But control logic absolutely depends on the previous input, because there is something called as a state. What is the state in which the microprocessor is operating? Okay, when the new inputs come, the next state depends on the current state. So control logic, generally it is implemented by something called as a finite state machine. So if you are doing ADLD, Advanced Digital Logic Design, you will definitely learn about finite state machine there. We will not do too much of that here, but here memory is required, that is the state. Okay, it might be a sequence of numbers, and that particular sequence of numbers will be stored in a memory unit, and when the new input comes, it will check the state. Okay, then it will go to the next state based on the value of the current state. It might go in two different directions. If it is 0 0, it might go here. If it is 1 1, it might go here. But there the state or the current operating conditions matter a lot. So there the functionality is by sequential circuits. So here of course we are not going to look at that, completely different type of functionality. And this diagram is very important because all modern digital systems, okay, they operate in this way only. So this is a partition. Okay, our modern digital designs are very, very complex. Nobody does all our things that we do by hand, all these simple logic functions and all that we are talking about. Nobody does them anymore by hand. Right? We need to know the basics, of course. So whatever we are studying here is very important. But at the industry level, right, everything is done using tools, and the logic blocks, okay, they are partitioned. If you have a design that is, say, having a video processing unit, that is having arithmetic logic unit, that is having some channel coding unit, these all are practical blocks in all modern designs. Okay, because they have some requirement as part of the design. For example, if you take an Intel microprocessor will, you might have even definitely read this if you have investigated the specifications, but they will have some inbuilt graphics capability, which means that one of the most important functionalities of any microprocessor, okay, if you just use it for general purpose usage, like your personal computer, you might play some video games, you might watch some videos, you might browse the internet. But in all of these, it should be able to render the screen nicely. One of the most important functionalities for the product to be successful, right? Not any specialized use, just the basic uses. It should render the images nicely, images or videos. So almost all microprocessors today, okay, I'm not talking about the GPU. GPU is completely different. That is by itself, that is a integrated circuit. Okay, I am talking only about the CPU. Inside the CPU, there will be a graphics processing unit or a video processing unit. That might be this unit. Okay, video processing unit might be, say, 10,000 gates minimum. I'm sure it's more than that also, but 10,000 gates might be the size of the video processing unit. So the input is going through the video processing unit, okay, and before it is directly given to the next block, because what is the output of this video processing unit? In image processing, you might learn that everything is divided in terms of pixels. So your screen resolution, for example, if you have a 1080p screen or a 4K screen, now even 8K is coming, right? So 8K screen means the number of pixels will be enormous. So the number of outputs here is basically the number of pixels, right? And each output, we cannot say when the output will be ready. One output might be ready quickly because it's in a corner of a screen. I'm not going to do any processing. Another output in the middle of the screen, I might do a lot of processing. So it might be ready much later. So how can I make sure that all the pixels are ready? If I pass improperly, then I might be doing something ridiculous like mixing 2-3 images that are from, for example, in a video is divided into frames. Suppose you mix the frames and show it to the person, he'll not be able to understand anything, right? So you have to make sure that one frame is fully processed before you send that out, and that is what this clock does. Clock doesn't allow partial outputs to propagate to the next combinational block. So the clock will stop it, okay? And when all the outputs are ready, we have to design the clock signal such that all the outputs are ready. Clock signal is not an automatic signal, right? Clock signal depends on the functionality that we have. And based on all the functionality, the designer might say, okay, so for this type of image processing or video processing functionality, you can have, say, 500 megahertz clock signal. So after 500 megahertz translates approximately to 2 nanoseconds clock, I think. So after 2 nanoseconds, okay, all the outputs here are ready, then the clock edge will come, and then this will be sampled and stored in this register, okay. And once it is stored in this register, this block will be seeing the output and it will be doing something during the next clock cycle. So this is the way in which most modern microprocessors are designed. Okay, we cannot have directly. So the beginning of VLSI itself, maybe around the 80s, around the 80s. Okay, asynchronous design was popular. That is, there was no clock signal. You give the input, you get the output. But there it was a much simpler world. They were not having so many blocks like we have today. So today, with the amount of complexity that is there, with the amount of interconnection, with the amount of parallelism, etc., it's very difficult without this kind of structure. We need to make sure that our signals are proper before we give them to the next block. What is the best? There's no other way. Can you think of one way, okay, to make sure that the signals are being synchronized properly before giving to the next block? It's not possible. There's no other way. The only way is synchronize everything to the clock edge. And this is also a perfect example of the locality rule. If you remember when we talked about the structured design strategies, try to make all the signals temporally local. So temporally local means all the signals should be ready at about the same time. When is that time? When the edge of the clock is coming. So this basically is an example of that. And since we are looking at this type of functionality, we don't want anything great here, okay. We just want a simple register that can store the value and pass it on, and it should be somehow connected to the clock signal. So it is not something that is very complex. It is just a simple store and pass. We don't want to do any computation, any modification, nothing. Only thing is, somehow it should be related to the clock signal. So that is what we are going to see, the simple D type functionality. So we are going to look at two specific sequential circuit classes. Okay, so let's draw some waveforms. Okay, so something I have drawn, I'm not even sure if it is correct or wrong, we will see, but we have two signals, a clock and a D, and I have drawn some vertical lines. This is basically telling us when the signals are changing, and based on the two signals, okay, we want to determine latch and flip flop. Okay, so the two most important functionalities in sequential elements are latch and flip flop. Okay, so latch and flip flop both are memory elements, both have a clock signal, but only difference is the latch is sensitive to the level of the clock signal, which means that as long as the latch, as long as the level is either high or low, that depends on the design, but as long as a particular level is maintained, the output of the latch will be continuously changing. That is, the data will be continuously passing from the input to the output. Okay, the flip flop or register, even though we had shown register always means flip flop, and it always means that it is edge triggered. Okay, it can be positive edge triggered or negative edge triggered. Sometimes it will be dual edge triggered also, but what that means is the data is passed from the input to the output only when the particular edge of the clock has arrived. The rest of the time the data does not pass. Okay, the data does not pass, and it doesn't mean that the output is at a high impedance state. That is where the memory functionality comes into the picture. The previous data continues to be shown at the output. The next data, when the data changes, when the next edge of the clock comes. Same here also, right? When the data is being continuously sampled, it will be coming to the output. When the data is not being sampled, the last data that was sampled will be available at the output till the next clock level comes. So memory functionality is definitely there, but the main difference is level sensitive versus edge triggered. So based on this, for these two, can you tell me which is which, the top and the bottom? You have to decide. Okay, so this generally directly will tell us if the output is changing when there is no change in the clock signal. This means that the output is sensitive to the level of the clock. This means that this is a latch. Okay, so the output is sensitive, which means that the output is following the input, and here comes the high value. So here the output stays at the previous value. Okay, it stays at 0, until the next clock cycle. So next clock cycle the data is high, so the output rises, okay, to match the data, and then again it starts following the data until the clock goes low. So it can't, sorry. So again, I knew I would have made some mistake. So here again it should rise with the data and continue. So this is a latch, and here we see that the data is changing, but the output is not changing because it is showing the previous stored value. When the clock edge comes, then the output falls. So basically here the clock edge triggers the output, and it continues at the previous value. Whatever the output is, input is changing, it is not coming to the output until we come to the next clock cycle where the input is high, so that goes high. Okay, so this type of functionality is called as edge triggered. Okay, in particular this is positive edge triggered, and this is a negative level sensitive latch, and these two are the circuits that we will discuss. We will not discuss any other types of circuits. So first we will look at the latch. Okay, in particular D latch, we don't want any complicated functionality or any logic to be implemented as part of the sequential circuits. Input equal to output. Okay, and you might ask, why do we need two? Why do we need latch and flip flop? Among the more popular ones definitely is the flip flop. Okay, more designs you will see that are edge triggered only because it makes synchronization easier. But in certain cases, if you have some problem with the timing, okay, then latch can help to a certain extent. So we will look at this more in the 5th unit, where we are going to be talking about purely about timing. But for now, both latch and flip-flop are almost the same requirement. It should have a memory and it should have a clock signal. But flip-flop is the more common one compared to latch. Okay, so we will look at latch first, and then we will look at flip-flop. Okay, so very simple circuit, and we just discussed these two, the transmission gates. So transmission gates are used for implementing the latch circuitry, and these two are nothing but our static CMOS inverters. So this back-to-back inverters, okay, they are, this is among the most fastest, not the most common, okay, most fastest way in which the memory circuits are implemented. And this circuit also forms part of what is called as SRAM, or static random access memory. And SRAM are the very highly optimized version of this thing, but still they are not used in, for example, you might have heard about solid state devices. Solid state devices generally they are very large. That is, you don't have 8K solid state device. Solid state device generally starts at 1 GB and goes higher than that. There, no, not this. Okay, that is a completely different technology. This particular memory implementation is popular where the speed is of utmost importance. More important than anything else is speed and power consumption also. In that case, this is the best option. And where this is implemented is in the okay, primary memory. What is primary memory? Any operation that has to be performed by a microprocessor, okay, directly the memory or the data will not go from the hard disk to the microprocessor. There is something called as a memory hierarchy. Hard disk is the furthermost, okay. From the hard disk, it will go to the RAM. From the RAM, it will go to the cache, or from the RAM, it might go to the main memory also, or what is called as the primary memory. So the primary memory is the one that is directly connected to the heart of the computer. And because it is so important for the overall operating speed, okay, primary memory has to be very fast. And that is where we use this SRAM cell or SRAM circuitry, back-to-back inverters. And this is very small. Primary memory, okay, might be as small as 8K. Okay, that is only 8,000 bytes. 8,000 bytes. Not in terms of MB. Your cache might be 512 MB or 1 GB cache. Your RAM might be 64 GB. Nobody works with 4 GB today. At least 16 GB, if not higher than that. RAM might be 16 GB, 64 GB, etc. And the hard disk might be at least 256 GB, 1 TB, whatever, right? But this is much smaller, 8K. But this implementation using this back-to-back inverters is the fastest implementation. Okay, why it is not used everywhere? Why can't we use this everywhere? Because of the size. How many transistors are required for this implementation? 4 transistors, and additionally there is some control circuitry also required. So for every 1 bit of memory, you need approximately 8 transistors, not approximately, exactly 8 transistors. So this is a little bit big when you are looking at gigabyte range. When you are looking at GB range, right, then this becomes too much. Then we go for different type of memory technology. Number one. Number two is also because these two are inverters, static CMOS inverters. Once you switch off the computer, the memory is gone. So these are examples of what are called as volatile memories. Okay, so we'll not go into too much about this. We are more focused on this part. Okay, so this back-to-back inverters is the memory functionality, okay, and this is the data functionality. So I can divide this into two phases of operation. So let us say I give it as clock bar, okay. So I can give any signal and its complement to a transmission gate, but remember that don't give the same here and here. Okay, suppose you're giving clock to the CMOS transistor, here you have to give clock bar and clock. And why that is like that is because we are going to divide the operation into two. One is, let us say that just like the waveforms in the previous diagram, we want to implement a latch that is sensitive to the negative edge of the clock, okay, which means that as long as the clock is low, the data should be continuously going to the output. So then I will call that as load phase. Load means load the data into the cell, okay, and this equivalent circuit will be D. The feedback part, okay, we don't want the feedback part to be happening because that could create a problem when the old data and the new data are not matching. Suppose I did not have this, I just decided that either I will be loading new data or storing the old data. Suppose I have stored data equal to, suppose D equal to 0, okay, which means 0 will come here, 1 will come here, 1 is here, 0 is here. So 0, 1 will be continuously recycled. But suppose here the new data is 1, then what will happen is this will pass it in the load phase and I will be left with 1 here, and that will be a problem because I am getting 0 here and I am getting 1 here. So what should be the value in the wire here? It will be at an indeterminate value. So to avoid that, we divide the operation into two phases. That is why we need this second transmission gate. This is not a, this is a requirement to avoid this type of intermediate value voltages, and that is why we basically disconnect, okay, and that is also why the clock signals are opposite phase of this one. When this transmission gate is conducting, this should be open circuit, and if I design the clocks in that way, then this will be conducting, this will be open circuit, I am loading. So now continuous connection is there. As D is changing, there is no clock signal anywhere in this diagram, right? Clock is completely out of the picture. When clock equal to 0, continuously D is sampled and its complement is being passed to the output. So this is the load phase where the new data D is being loaded into the memory. Where is the memory? Here, okay. And in the store phase, in the store phase, our memory transmission gate is conducting, input transmission gate is not conducting. That is when clock equal to 1, you can analyze these two transmission gates. When clock equal to 1, the input transmission gate will be open circuit. So that means that the memory functionality comes into the picture. This is just storing the old value of D and continuously giving that at the output. Whatever changes are there happening in D, they are completely blocked by the open circuit here. So they will not be reflected in the output. So the clock equal to 1 phase, the D is completely blocked. We don't sample the D at all. So then what is happening? the old value of D is continuously stored in the back-to-back inverters available at the output. So this is a very simple functionality, very simple operation also, the latch functionality. So we should be able to do it for any phase. So one question I can give now is design a okay. Show the functionality with waveforms. This is the same for latch and flip-flop. Okay, any design, two things they can ask: the circuit and the functionality. Functionality, you can write lines and lines of explanation, but the better way to show it is by showing sample waveforms. So just like we did here, okay, not this, before that, draw a clock signal and a sample D, and based on your circuit explain the output, and that will prove directly to us that it is sensitive to the positive clock cycle or the negative clock cycle. This one is a negative clock cycle. So if I draw the waveforms, if D is changing in the negative clock cycle, I should be seeing that in the output of my flip-flop. Okay, so this type of question is what you will ask in the test and the exam. So this is the first circuit, and a very slight modification of this, we can go from latch to flip-flop. Okay, so instead of, this is again one of the principles of regularity, instead of starting from scratch and designing completely new circuit, if we have a good circuit with good functionality, proven functionality for a latch, we will try to reuse that and get a flip-flop, and one of the results of that requirement is this circuit. So there are other ways also. This is not the only way in which we can make a edge triggered flip-flop. There are other ways also, many other flip-flop circuits are there, but the one that we are going to study is this one. Okay, so basically what we do is we take two latches and connect them back to back, but the latches are not the same. What is the meaning of they're not the same? Okay, the circuit is 100% the same. What is the difference between the two? The difference between the two is in the clocking scheme. So I can decide that. Okay, so let's say that I give clock bar. Once I decide this, then I should give the opposite here. I cannot give the same thing, right? Because that is one of the requirements of the latch. So clock I am giving to the PMOS, which means clock bar and clock. And here I should give the opposite of the first latch. So here I am giving clock and clock bar, means here I should give clock bar clock, and automatically whatever you give here from the latch functionality, you should give the opposite here. So here you will get clock. Okay, so this is a master slave configuration, and I don't know what is the meaning of master slave. It's just terminology. The main functionality is there are two flip-flops. Okay, and if one flip-flop is in load, okay, the other flip-flop will not be sampling the output, because the output of the first flip-flop is given to the second one. So if new data is being loaded into the flip-flop, this one is not going to see that data. It will be storing the old data. When this, sorry, not flip-flop, latch, when this particular latch is in store mode, then it will be seeing the data, and that will be coming to the output of the second latch. So one direct resultant of that is, in the store mode, the data cannot change, because the store mode is storing a constant data. So that is why the D, whatever changes are there, they are never reflected directly in the output. They are reflected only during the next clock edge. Okay, so let us draw the waveforms and determine whether this is positive or negative edge triggered. So we will take some sample clock and D. Okay, and one thing is, if you want to determine something whether it is positive or negative edge triggered, you put different values at the edges. If you put the same value, then you will get the same thing. You will not know whether it came from the positive edge or the negative edge. So let us take this D, okay, and change it here to 0. So in one edge it is 1, and in the negative edge it is 0. So that based on the value that we get, we might know. Okay, so here we have 2. Directly we cannot get Q. First we have to plot QM, and from QM only we will get Q. So first is we will plot QM, and we know how to plot QM because this is just a latch, and for this latch we can say which is load and which is store. When will this particular latch load new data? When clock equal to 0, right? Because clock equal to 0, it will take the new data. When clock equal to 1, it will not see this, it will be storing the old data. So that much we know. I can draw QM. So let me draw QM. Okay, so when clock equal to 0, I should load. So clock is equal to 0 up to this particular point. Okay, and clock equal to 1, it is store. So I will not see. Okay, I think that is correct. I hope that is correct. We'll see. Clock equal to 0, data is coming here. When clock goes high, the store happens, and this particular is not seen in the output QM, and it continues, and again when clock goes 0 it starts sampling and then the data goes low. So now I have QM. Okay, now I can forget this part. Now I just consider this as a new latch which is load and store. Here it should be opposite of the previous one. We can check that also. When clock equal to 1 it will be loading. Okay, and when clock equal to 0 it will just be storing the old data. Okay, so now I don't care about this. I have my QM signal and this functionality I can get the output Q. So QM is here, so I will see. Okay, and clock equal to 1 is load. So up to this particular point I don't know what is the value. Okay, because only when clock equal to 1 it will get the value from QM. So clock equal to 1 is load, and whatever is in QM that will come here. QM is not changing, so QM stays at a constant value as long as clock equal to 1, and when clock equal to 0 this is just storing. Okay, clock equal to 0 is store, so QM equal to 1 that has come here, and I'm continuing to store that. Again when clock equal to 1 I am getting a load, so at that point that will come at the output. So from this analysis, okay, we have the waveform. So from the waveform, now can we decide whether it is positive edge triggered or negative edge triggered? It is a positive edge triggered flip flop, because whatever data is there, okay, at the positive edge of the clock cycle, we don't care about QM. Whatever the data is there at the positive edge, that is coming. Whatever data is there at the positive edge, that is coming. So therefore this is a positive edge triggered flip flop design. So next question logically is negative edge triggered. What do you do? Start from the first transmission gate, all the transmission gates opposite. Make this opposite, this will change, and this have to be matching. You might have realized by now, when this latch is in
No problem. Okay. 4:30. But I just yesterday or okay. Not instead. She was at some other time, but